So, welcome everyone. Thank you for joining us today. This is the Low-TRL Renewable Energy Technologies Workshop. Just as a brief introduction, let me see if I can move slides. Okay, so today we're bringing together six European projects that they are both in the research phase. They were all funded under the same call topic from Horizon 2020, focusing on developing the next generation of renewable energy technologies that will be the backbone of the energy system in 2030 and 2050. All these technologies, even though they are very different from each other, they are all new, more efficient, and cost competitive energy generation and conversion technologies. And they are all around the research phase in TRL 3 or 4. Um, so yes, I'm going to briefly present the agenda. First, we're going to hear the presentations of each of these six projects, which are region by two. We have here Ricardo Camerano from Tifeo, which is the startup holding the patent for the technology that is running the project. Then we'll have the City Solar project with Aldo Di Carlo from the Italian National Research Council, which is the project coordinator. We also are missing right now Brian. I think he just joined, so that's perfect. Welcome, Brian. He's representing the selection to of Starklight. And finally, we have Stefania Privitera from the Telegram project, representing the Italian National Research Council. So we will hear from each of them a brief presentation of their projects, and then we will have a panel discussion where we'll have different topics for them to discuss from the common points that they have on their projects. So I will welcome Ricardo to the stage. Okay, let's see. Do this. And I will switch presentations. Uh, mm, 1 second. Let's see. I'm struggling to see it. Okay. It's a bit difficult to see from here, actually. Okay. Can you all see our screen? Okay. I think this should be okay. Okay. So welcome, Ricardo. The stage is yours.
Okay,
You
thank you.
have 6 minutes to present the region-based project.
On this way, okay. Okay, good morning, everybody. Can you all hear me? Okay. Good morning again, and thank you, Laura, for your introduction. My name is Ricardo Camerano, and as she said, today I'm representing Regime Bachu Project, um, which is, Laura, can I see my presentation here, or is it not possible? Otherwise, don't worry, I just, yeah, I look at the screen, I know, no problem.
You see both here and there.
Okay,
Can you still see his presentation?
this is PDF.
Okay, this is the PDF. I think
Don't worry, Laura, I can look at the screen.
let's keep it like this.
Okay, okay, let's come back to the presentation then. So, from what you can see here on the screen, our project is about next renewable multi-generation technology and fluid machines. But actually, what are we doing? Let's see it. So, this is our concept. We all know that in the long-term European energetic scenario, Europe will be dominated by solar sources, wind sources, but they are all characterized by the fact that they will need a reliable natural input to work. And this leaves gaps that have to be somehow filled. when such sources are not available. Our target is to fulfill those gaps, converting any type of heat source into energy vectors. Energy vectors are heating power, cooling power, and electricity that, in our vision, have to be available anywhere for any kind of district of residential units at any time with no need to have sun or wind and have to be flexible to meet the energy load demand. So everything started out in 2018 when the startup Tifeo patented a novel thermodynamic cycle which was demonstrated to improve the efficiency, thermodynamic efficiency of thermal machines. The patent was accepted nearly worldwide in seven macro regions, and that formed the base of our project. What you can see here on the right hand side of the screen is our goal. By 2024, we are planning to build something that will look a bit like that. Well, hopefully not that big, but it's going to be made of pipes. It's going to be made of rotating machines, heat exchangers. So it is a power plant looking from the outside. Our target is to demonstrate the adequacy of our idea, of our ideas for district heating and cooling. And we also want to develop a mechanical technology for such a cycle. Moving on, the project is organized by a logical way in three major phases. In the first one, we are carrying out the design part. We are uh, realizing the design of the plant. In the second phase, what we designed in the beginning will be built. We are going to be hosted in Pisa by the University of Pisa. And after that, there is going to be a test session during which we'll see if our ideas will be confirmed, if we can demonstrate its viability and its performances. Even if we are still at the first year of the project, this is for us month 14, we already submitted the first deliverables. So we produced the first results. And they mainly have to do with the conceptual phase. A few slides before I show the thermodynamic cycle, we moved from that conceptual idea to an optimized design. And based on that, we are developing the future plant. So a process flow diagram was already built, and that is forming the base for a risk analysis that in our project has a fundamental importance because we are dealing with refrigerant fluids under pressure at high temperatures. So the risk analysis is a fundamental step. And in parallel with this, other partners of our project are designing the two-phase machines able to work with two-phase mixtures indeed. So a quick look at what we are trying to achieve. So if on the one hand, we are focusing on developing technology, reaching TRL4, at the same time, on the other hand, we are planning our future. So we are aware that for sure we will need further research to improve the technological level of this technology. But at the same time, we are gaining a deeper knowledge of the market on what user needs and how to penetrate the market to reach the users. So last, but of course by no means least, I'd like to introduce my partners, the partners of the project. I'm very glad to represent them today. And a special thanks goes to Tifeo, the startup I'm an associate of, because without them, wouldn't be possible to have this project. So thank you everybody for listening. This was our project.
Thank you very much,
Thank you,
Ricardo.
Laura.
Oh, yes.
Excuse me, it's for LinkedIn.
Yeah, yeah. Do you want me to switch to another slide? Okay, perfect. Thank you very much, Ricardo, for this presentation of the Regime by 2 project.
Laura,
Yeah,
we weren't able to see the presentation, the slides.
you were not able to see the presentation.
I couldn't. No,
Was it the problem for all of you?
I think so. Yeah.
Okay. Wait a second. I'm sorry for this. Are you able to see it now? Yes?
Yes, yes.
Okay,
Yeah.
let's see. 1 second. Now we're going to the City Solar project. So now I welcome Aldo to the stage. Okay. Wait a second. Please confirm if you can see the slides. Second. Pedro, could you please confirm if you can see it now?
I can, yeah.
Yes, okay, perfect. Thank you very much. So I welcome Aldo Di Carlo from the CNRS. No, is it?
CNRS,
Yeah,
yeah,
I don't know.
CNRS,
It's
yeah.
in the
For the
acronyms.
movement there.
Yes. So I let him start with his presentation. You
Thank,
have 6 minutes.
yes, Laura. Thanks a lot. Welcome everyone. I'm Aldo Di Carlo from University of Rome Tor Vergata, but for the moment I'm in CNR, and I'm the coordinator for the project City Solar, which is dealing with a problem. The problem is just showing in the next slide. Oh, here. How? Not changing. Okay. Thanks, Laura. So the problem is the following. So we should know that buildings are consuming much part of energy, and they use almost 40% of energy produced, for example, in Europe, and they impact for 36% of greenhouse emissions. So every action we do for a building to reduce the consumption of energy in buildings is very important. Actually, we need to push a building to move toward nearly zero emission building or more to positive energy building. So for this reason, the idea is to provide buildings with active facade where they can convert energy by exploiting solar conversion. So for doing this, I mean, and if we are thinking about a glass facade building, we need to develop something that could produce energy exactly in the building where we are using the energy. So the idea is to use transparent photovoltaics for facade. So we need to work with the transparency of the photovoltaics, efficiency, color, and social acceptance. These are important goals which are quite demanding, and this is what the City Solar project would like to solar goals are summarized in this photovoltaics that is able to achieve a power conversion efficiency of more than 15%, should have an average visual transmittance larger than 50%, and should have also color neutral, or should be able to tune the color as much as we like. So to do this, we set up a consortium at the European level, which comprises of research institute, CNR, CNRS, and the University of Rome Tor Vergata, and FAU, which is German Nuremberg University, and a small medium enterprise with brilliant matters, and Eni and ADF, two large company which are really devoted to make this green transition. We also involve KAUST because this project is within Mission Innovation, so KAUST from Saudi Arabia and Brilliant Matter from Canada. So the idea is the following. So we use two technology and we laminate two technology together. So we have a top solar cell which is absorbing in the near UV, and a bottom solar cell which is absorbing in the infrared, near infrared. So all the visible radiation is left untouched, so we can see through the window, and we laminate this together in a flexible substrate. Is a multi-junction. So for the multi-junction, we can go beyond the Shockley-Queisser limit. So what is natural, what is the limit for single junction like silicon, for example. So, and at the very end, city solar, you see, it will place as a star in the diagram. So the efficiency and the average visual transmittance should be, as I said, and should be represented beyond the state of art. So these are the simulation we have done. It's indeed possible to reach this goal, and consortium is now moving to the realization of this kind of photovoltaics. To do this, I mean, we will develop perovskite top cell, bottom organic infrared absorber. We need to do also light management, which is very important. So we will use the distributed Bragg reflector and also up conversion as well. And then we have a registered way to connect the top cell and the bottom cell. So thanks a lot. This is the project.
Thank you very much, Aldo, about this important technology. It's very fitting this conference. We will have time for questions at the end, but so we run smoothly with the time. That's why we're passing presentation by presentation. So next one in this view, let me see. Yes, we can hear you. Would you like to share your slides, or do you want me to share it from here? You hear me?
Sorry, were you talking about select CO2? Can you hear me? Hello? Can you hear me? Can you hear me?
Yes.
Ah, okay. With respect, if you have the slides up, that would be nice. I'm having some internet issues. So if you have do you have the slides to present, or otherwise I can bring them up?
I do have the slides, so I can present them. Is that I would like people to see you at the same time as they see the slides. Let me see, how can I do this? Okay, it's complex to see it from here. Okay, but now I have to look for your presentation, which is here. Okay, it's in the other side. Can you see your slides?
Yes, I can see it.
Can you see them in full screen mode or not?
No, the other mode.
I don't know how to do this. I'll try with the PDF version. How do I put it full screen mode? Can you see them in full screen mode now?
Yeah.
Just wait a second. I would like to switch this so they can see you. Okay. Okay, perfect. So you can start now. You have 6 minutes. So I welcome Brian from the Select CO2 project.
Yeah, so what we're trying to do with our project is basically do CO2 electrolysis. So take carbon dioxide, water, and electricity and get some type of product. Now, it selects CO2, and the reason it's called that is because we want to selectively choose a certain product. So we have 3 kind of different catalyst focuses, one for carbon monoxide, one for ethanol, and one for ethylene. And we like these because in the chemicals industry, they're really huge chemicals, and there's a lot of benefits with that. We're primarily a bunch of universities. We do have Denora, which is a company, and RENA Consultancy, which obviously is a consultancy company. But because we have a bunch of universities, it is a low TRL level project. Laura, would you mind flipping to the next slide? Oh, is this the PDF copy?
Yes, it is.
Yeah, this is a little hard to say anything here because I had two figures overlapped. Yeah. Let's just go to the next slide. That's just not working with that slide right there.
Would you like to go to the PowerPoint now?
So what we're trying to do here is so we have three groups that are focusing on catalysis. We have a group from Berlin that's focused on carbon monoxide. We also have a group here at DTU where we're focusing on ethanol, and we have another group with ethylene. Now, when we're making these electrolysis devices, in general, a lot of the principles are the same. I mean, we're all bringing in CO2 as a product, and on our counter reaction for all of these, we're doing oxygen evolution. So the CO2 reduction is our cathode reaction. But we do need to have some things that are uniform. So we all need to have a gas diffusion layer to allow our products, our reactants and products to come in. And Denora is helping us out with that. And it is pretty uniform among the three different products we're going after. There is a slight difference, but we do get some synergies there. Also, we need to have a membrane to separate it. And in doing that, we're basically using an anion exchange membrane. It keeps us alkaline, and that favors our catalysis. And it is good to make sure that we're working with that because alkaline exchange membranes are kind of a young field. And the final thing we're doing with respect to our devices are modeling our mass transfer. So obviously you need to have good mass transfer, and that's what we're doing. And then at the same point, in the same project, we do have RENA Consultancy, which is doing our social societal impact, I guess. So we're looking at techno-economic analysis. We're also looking at life cycle analysis, trying to figure out what markets these products can go into first, and kind of basically where is the best bang for our buck with what we're trying to do here. But again, this is a low TRL level project, a TRL 4, and we're just really trying to get these devices and see what's the potential of these devices. If you flip on to the next slide, I can kind of show you what's important to us and what kind of our discoveries have been so far. So our first discovery, and kind of probably our best or our most important one, is that we're getting CO2 to CO catalysis at about 99% selectivity at relatively high current densities. And as I'll show in the next slide, about 200 to 300 is kind of where we need to be minimum for commercial viability. And our other 1% is hydrogen evolution. So it's not that bad, but it is nice that we have a unit that can be very, very selective to CO. We're also working on recycling our products. So especially when we're trying to produce ethanol and ethylene, carbon monoxide is actually the first intermediate. So if we try to do CO2 reduction and we don't get it completely reduced to ethanol or ethylene, we can recycle that carbon monoxide back around and re-reduce it to whatever we're trying to get, whether it's ethylene or ethanol. I said earlier that the membranes are something that we're trying to work on our durability. We've been able to get them to 200 hours in our field with what we're doing. We're pretty happy with that. And then we're also using the same catalyst. It's a copper catalyst for both ethanol and ethylene. So we have to figure out how we slightly modify that to get ethanol and ethylene. And we figured out mechanistically where the branching point is. And that will now allow us to go a little more in depth in trying to optimize the splitting to either ethanol or ethylene. Could you go to the next slide? So to put this all together, how we get to commercialization. So basically we need to be 300 milliamps, our low end. We'd like to be at about 1 amp per square centimeter for our devices. Right now we're at about 300 milliamps per square centimeter. You see our product distribution over there to the right. There's about 10 different chemicals. And that is what we're trying to do, eliminate these. They're all pretty valuable, but we're trying to eliminate these as much as we can. Once we have that, we go to a single, basically, paper, and then a paper size, and then we kind of build that up a little bit, and then we stack a whole bunch of those together until we get, bigger and bigger, devices. and then we have something industrially viable, when we're over at the megawatt scale. So that's I think that's all I have with respect to our project, and yeah.
Thank you very much, Brian. Thank you for joining us and for explaining this very important technology. Let me see. I don't have more going to hear from Pedro Cermeño about the Prodigio project. Pedro, would you like to share your own slides? Would you like to
I will share.
Okay.
By the way, Laura, we cannot hear you very well.
You cannot
Probably you need to be closer to
Can you hear me well now, or is it
Yeah.
a connection problem?
No, it's just you were too far from the microphone.
I cannot hear. Okay. So
So can you see the presentation? Can you see it?
yes, we can see it now.
Okay. So I will present the project Prodigio, developing early warning systems for improved microalgae production and anaerobic digestion. This is a 3-year research innovation action aimed to boost the production of biogas from microalgae biomass. So basically, in this slide here, in this diagram, here we show the circular microalgae to biogas production chain explored in the project, illustrating the 2 different conversion stages from solar energy to microalgae biomass and from biomass to biogas via the anaerobic digestion processes. So the main problem that we are currently facing with these conversion systems is that no one of them is functionally optimized for large-scale applications. So on the one hand, microalgae production systems are affected by pests and diseases that, as in the case of agriculture, cause significant economic losses. On the other hand, the anaerobic digestion process is affected by biochemical instabilities associated with changes in the ecology of the microbial communities involved in the biomass fermentation and methanization processes. So process monitoring is a crucial task for bioprocess optimization. However, these monitoring technologies are seriously underdeveloped as far as microbial-based production systems are concerned. So in Prodigio, the main objective is to establish a base of knowledge for the development of a system failure prediction technology that increases the performance of microalgae production and anaerobic digestion systems and advance toward more sustainable production of biogas from microalgal feedstock. So ultimately, the goal of Prodigio is to bring the TRL from 1 to 3, proof of concept, by demonstrating the efficiency of early warning signals in predicting as far as in advance as possible the failure of microbial-based production systems. So the project is based on these different specific objectives. They include experimental, such as simulation of the failure of microalgae production and anaerobic digestion process in lab-scale bioreactors, and different methodological, mathematical analysis to identify the early warning signals that allow us to predict when the system is going to fail. So basically, the process stability is critical in nonlinear dynamical systems, such as ecological systems, where the functioning of complex microbial communities controls the performance of the system. So these dynamical systems can undergo state transitions from one stable state to another at a critical threshold, also called the tipping point. So what is important is that near the tipping point, the systems typically exhibit some statistical signals, such as a slowdown recovery or high variance, which have been proposed as warning signals anticipating the failure of the system. However, the effectiveness of these statistical signals as early warnings in a real system has been questioned. Basically, the main concern is that existing methods based on these statistical signals do not take into account the fact that real systems, such as ecological systems, are made of multiple interacting components. So, okay, this is a more realistic representation of real systems that show the changes in the topologies of the interaction networks over time. So it's here in the pre-failure state or tipping point that we can identify the main triggers of the failure of the microbial processes. So in Prodigio, we are currently operating algal reactors and anaerobic digesters to simulate the failure of microalgae production and anaerobic digestion processes. So we are generating long time series of routine measurements, including disolved oxygen, biomass production, dissolved organics, biogas production, etc., many other routine variables, but also specific variables such as chemical fingerprinting, resolving thousands of chemical compounds, metabar coding, describing the taxonomic composition, taxonomic structure of microbial communities in the bioreactors, and metagenomics, metatranscriptomics, and metaproteomics to identify industrially relevant genes and functions involved in the performance of these systems. So all this data are processed using our own bioinformatic pipelines, and the results are analyzed using state-of-the-art methods, mathematical methods for the reconstruction and interpretation of causal interaction networks. So in particular, we apply empirical dynamic modeling, which is a method for the modeling of nonlinear time series data. So EDM computes from time series data the causal interaction network on each time step. The time-varying interaction network provides an estimate of the stability of the system over time, allowing us to identify the main contributors to the failure of the processes. So with this, by combining this massive data acquisition and EDM, we will be able to carry out an unprecedented analysis of interaction networks, what we call the bioreactor interactomes, and efficient early warning signals for process failure in bioreactors. So the expected impacts of the project include, well, to improve bioreactor process and control systems, achieving TRL3, that once implemented will increase the efficiency of solar energy conversion to biogas. We will advance our understanding of the genes and stress response patterns of industrially relevant microbial guilds. Improved monitoring and forecasting capabilities will contribute to cost reduction of biogas generation, and increased resource and energy efficiency will contribute to reducing greenhouse gas emissions. So finally, the early warning signals identification method developed in Prodigio is applicable to the identification of early warning signals in other bio-based production systems within disparate fields, including bioenergy, but also pharmaceutics or nutraceutics. So this is our consortium. The project started in January this year and is a 3-year project with including 8 different research organizations. Okay, so that's it.
Okay, thank you, Pedro. You could not hear it, but they were clapping here in Rome. I was muted. Let me see, like, it was very nice to hear, like, not only that the importance of developing the technologies themselves, but also how to control them in the way that they improve their performance and reduce the costs. Let me go now. It's the turn for William, for Bill. Would you like to share your screen, Bill? I don't know if you can.
Okay.
Can you hear us, Bill?
Yes, I can hear you.
Okay. We do not see your screen yet.
No, I'm just.
It's all black.
Hang on.
Just do what you did before to share it in full screen.
Sorry. Seems to be a problem here. Let's try again. Oops.
I'm not sure.
So this doesn't seem to be working, Laura.
Let me stop sharing.
I seem to have. Wait a minute.
Is he there? Not anymore. I cannot see from here.
No. My screen's. I can't even see.
And we cannot see your screen. Try to stop it and share it
Wait a
again.
minute. Okay. I'll stop sharing and then I'll try again. Right. I've gone for. Oh. Right. Okay. Has that worked?
No.
No? Okay. I think I'll just have to resort to you showing the slides.
Should I share your slides?
Yes, I think you should. I mean, there's an animation on them, which I guess won't work, but we can. We'll just need to go to allow. We'll just need to go that way. So I'll stop sharing, and you can show them.
Okay. Can you see your slides?
No.
1 second. Can you see them now?
Yes, I can see them now. Thank you.
Okay, perfect. So you have 6 minutes from me. Thank you.
Okay. Well, good morning, everybody. As you can see from the title there, that this project is about a new concept for a wind turbine. It's called the X-Rotor for short. It's a consortium of the partners are shown at the bottom of the slide there. It's myself and my team at the University of Strathclyde. The other partners are Delft in the Netherlands, Sener in Spain, NTNU, this is the Norwegian University of Science and Technology at Trondheim, and UCC in Ireland, that is University College Cork in Ireland, and GE, who are one of the largest turbine manufacturers. The next slide, please. Laura, can we have the next slide? Oops. Laura, do you hear me? Well, I'll just need to thank you, Laura. Now, and first, this is an animation, and if the picture on the left indicates the turbine working, you can see why it's called an X-rotor. That there is a large, instead of the normal type of wind turbine, which has a propeller-shaped rotor which rotates around the horizontal axis, this has an X-shaped rotor which rotates about the vertical axis. Although the resolution of this is rather poor, if you look very closely, you'll see there are additional rotors attached to the bottom of the two lower arms. On the right, it shows one of the properties of this, and that those smaller rotors are quite close to the surface of the sea. Next slide, please. So you can perhaps see it clearer from this. But the primary rotor is called the big X rotor. That rotates around a vertical axis. And there is normally the main rotor would be attached to a power takeoff unit. It could involve a gearbox or a generator, and this is a very large. That is a very large and expensive part of a wind turbine, and it's also very heavy and usually at high height, tall, 100 meters above the sea or whatever. But the only thing we have at the heart of this rotor is a bearing. There's no power to take off directly from that primary rotor. The secondary rotors are really quite small, as you can see. They rotate very fast as a consequence. And again, this is much simplified. There is only a generator, a conventional generator attached to those smaller secondary rotors. That is one of the potential advantages of this concept, because it makes the power takeoff very much cheaper. It reduces the cost of the power takeoff by about 75%. Next slide, please. So we did a preliminary study. We got financing from the Engineering Physical Sciences Research Council in the UK, which funds scientific research in universities. And we were able to do a feasibility study about 3 years ago, which took a very basic look at this concept. And we estimated the savings for the capex, the capital cost of the turbines. There are additional other savings, but the main saving is the reduction of, as I said, 75% of the power takeoff. Now, for a 5 megawatt turbine, that would amount to about 700,000 euros. So it's quite a saving. But it depends on the type of turbine. The chart on the right there shows the capital saving on this turbine from conventional turbine, and it rises from about 5% for what's called a 3-stage defig approach to power conversion, up to about 30% for direct drive permanent magnet generators. Next slide. Thank you. But there are additional savings. As I mentioned earlier, this is a much simplified turbine. That means that obviously the failure rates and components, we anticipate that will be lower, but we haven't taken that into account and making an estimate of the operation and maintenance costs for this turbine. What we've taken into account here is that all the large heavy components, there are no large heavy components. On a typical turbine, 500, 5 megawatt wind turbine, the weight of the components, like a generator and a gearbox, would be several hundred tons at the top of a 100-meter tower. Our total weight for the power takeoff is about 10 tons. So it's much, and it's maybe 20, 30 meters above the sea. So it's low weight, it's near the sea, no heavy lift vessels are required for maintenance and repairs. There's easy access to all the components, and as I said, anticipate to be more reliable. And that gives you the savings cost on from that aspect on the graph on the right. So now we've got the opposite behavior. For a 3-stage defig, the savings costs are about 50% on O&M, and it reduces to 24% for a direct drive PMG, permanent magnet generator. So overall, the savings here, the potential is quite good. There are other things to take into account, which is the efficiency of the power conversion. That, in essence, is a little bit less, but there's ways in which we can mitigate that problem. Next slide, Laura. So what we anticipate from the preliminary feasibility study, we had the potential here to reduce the cost of energy by about 20%. There are other advantages to this approach. It's much more scalable. And what I mean by that is that for a conventional wind turbine, as they get bigger in size, the cost of the power takeoff rises much longer than linear. So, but here, if we go to a bigger wind turbines, all you need to do is introduce more secondary rotors. You can double the power rating, just double the number of secondary rotors and their power takeoff, which just doubles the cost, which is better than for a conventional turbine. It's perhaps really well suited for floating because overall mass is much less. The center of mass and thrust is lower, so the requirements on floating platform and anchoring systems is much less. It's also got the potential to have much reduced radar cross sections. Conventional turbines do interfere with radars, and this is a problem for maritime authorities and defense. So, okay, next slide, Laura.
Okay, and if you could wrap up in
Yes, this is the last slide, absolutely. So the objectives of this project is to progress the concept through to about TRL level 3. Now, unfortunately, this technology is very different from previous turbines, so we don't have a design codes or tools. The existing ones do not apply to it, so we need to develop those and to be able to do a much better assessment of the concept to confirm the CapEx savings, OpEx savings, and the cost of energy reductions. Thank you for listening.
Thank you very much. Thank you very much for your presentation. Okay. Let me stop sharing if I can. Okay. Okay, it's giving me some trouble. So next we have Stefania Privitera from the Telegram project. Let me see if I can. I need to stop sharing. Stefania, will you share your own slides? Yes, perfect. Okay. So welcome, and you have 6 minutes for your presentation. Thank you.
Sorry, it seems. Can you see?
Presentation now, yes.
Okay. So good morning. I am the project coordinator of Telegram, which is toward efficient electrochemical green ammonia cycle. And I work at the Institute for Microelectronic and Microsystems of the National Research Council in Catania, Italy. The project was started in November 2020 as a duration of 42 months, and it is funded within the H2020 program by the CINEA. The other partners are Helmholtz Zentrum through the PV-Comb institution in Berlin and Forschungszentrum in Jülich, both are two German institutions, and Uppsala University in Sweden. So let me give you a very short background. The production of ammonia presently occurs through an industrial process which is called Haber-Bosch, in which hydrogen gas and nitrogen gas react at very high temperature and pressure, and mainly hydrogen is produced by steam reforming. So for this reason, this process of ammonia production is responsible every year for about 1 or 2 of the total CO2 emissions worldwide. So there is the need to reduce the impact of such a process. But moreover, ammonia potentially is a very good energy vector because of its large hydrogen content, high energy volumetric density, and unlike hydrogen, it is easy to liquefy the ammonia. So for this reason, it can be used for energy storage, in particular to mitigate the intrinsic fluctuation of renewable energy sources. So the goal of the project is to demonstrate at the laboratory scale a complete green ammonia carbon neutral energy cycle. So we start from renewable energy sources. We use the power to supply an electrochemical reactor that will produce ammonia, and then this ammonia will be used in a fuel cell in order to get back again electricity. Of course, this innovation requires the development of 2 key enabling technologies that are presently not available, and we will reach probably during the project at TRL over 3 or 4. So the first one is the electrochemical cell for ammonia synthesis. And in the project, we use a multi-stage membrane reactor, which starting from air and water will produce ammonia at temperature below 100 degrees centigrade. Then the second technology is the direct ammonia fuel cell. So we will develop a fuel cell which starts directly from ammonia without cracking and the separation of nitrogen from hydrogen, directly from ammonia in order to produce electricity. There are some challenges related to the development of these 2 technologies that will be impacted by the project. The first one is the development of novel materials, because novel catalysts need to be developed and implemented for the ammonia reactor and also for the direct ammonia fuel cell. We focus on high entropy alloys and on nanostructured heterogeneous catalysts. Moreover, it's very important to use low-cost catalysts and also sustainable materials. So we reduce as much as possible the amount of noble metals used as catalysts, and we employ mainly earth-abundant materials. But of course, these materials have also to be reliable and stable within the ammonia environment. And a further challenge is that we develop 2 systems which have to be compatible with the renewable energy sources which are fluctuating during day and during the year. So the electrochemical ammonia will be powered by these renewable energy sources, has to be stable with this fluctuation, and it will be coupled to the fuel cell in order to demonstrate the complete ammonia energy cycle. And we also take advantage of synergies with various stakeholders. For this reason, we have established an external advisory board, which include different stakeholders from energy provider to green hydrogen fuel provider, hydrogen and ammonia fuel cells, and also technologies for electrodes and water. Thank you for the attention.
Thank you very much, Stefania, for your presentation. Now we will begin with the panel discussion, when you bring the perspectives from each of your projects on several topics that we thought of. I will welcome Ricardo and Aldo back to the stage for the panel discussion. There's a technical issue that we do not have chairs for both of them. I can just stand, that's okay, but let me first share. But I think they're all, okay, it's very, okay, perfect. That would be perfect. Let me share my screen so everyone can see the questions. I am able to. Okay, I need to put this back here. what I want to do. Okay, we'll share my screen if I'm allowed to. Okay, one sec. Can you see my screen online?
Yes.
Okay, perfect. I will put it in. Can you see it in full screen mode? Can you see the questions? That's, I think you cannot. Sharing. Okay, I will not share in full screen because it seems to be giving problems. But seems that you're not. Okay, now it's ready. Okay, so thank you everyone for listening to these 6 projects. As you could see, they were very different from each other in terms of the technology that they were developing, but they did have some common aspects as the fact that they're all in this research phase and they can share some challenges, maybe not the most technical ones, but yes, the ones considering the development and bringing these technologies further. So we thought of 4 topics. We are having a few less minutes than we expected for the panel discussion, but let's try to cover as many questions as we can. And anyway, we will follow up conversations after this session, and hopefully next year's Sustainable Places Conference, we can bring in collaborations and see what we can achieve throughout the year. So the first question that we are bringing to the table is, how do you see that these technologies, these low-TRL technologies, will evolve in the era of distributed generation? How will they fit in the energy system of 2030 and 2050? So try to be specific about your project, but also considering what you heard about the other projects. So who would like to take the first comment on this? Okay.
Okay, can you still hear me well? There you go. Okay, good, good. So what can I say? As briefly said during the presentation, I think that the region by two technology is or can be integrated with more traditional renewable sources. Um, as mentioned, common sources like wind and solar, they will provide the backbone to the energy system. But because of their drawbacks, there will be need for someone to take those gaps and fill it with flexible energy. And that's where we'd like to put ourselves. We want to provide people with energy that can be democratic, that can be easily available at any time and everywhere. So, um, from our perspective, our technology is going to be integrated with others, rather than substitute current technologies.
They can hear me. Do you think this is also the case for the rest of projects present here? Can they be easily integrated with the rest of technologies already existing?
I can say something. So we have seen already in the presentation that technology could be thought in a way that they should be integrated. So I believe this is what is asking to us, and we need to move on in this direction. We have seen microalgae, we have seen wind that, as I said before, should be integrated with other generation of renewable energy. So all of these can be indeed integrate together. So, for example, for microalgae, see, for example, what we've developed, which is transparent photovoltaics, has been already shown that you can grow algae, microalgae, and at the same time you can convert all the radiation which is not needed by the grow. For the growth of microalgae, so you can increase in a tandem concept. I want to say you can generate photovoltaic energy, and at the same time you can generate biomass without losing in this combined use of the renewable energy. So I believe this will be the future. So I mean, the way we will invent how to integrate together this and let the people use it, because the social acceptance is also very important.
Thank you, Aldo. Maybe Pedro, you would like to say something as your project was mentioned.
Yeah, well, I agree with the speaker. So basically, I think it's important to integrate not only with other different technologies, but also with other different processes. In our case, in the case of microalgae production, we are trying to integrate it with wastewater treatment. So basically, wastewater has a lot of nutrients, and microalgae can grow very well in these water sources. So this makes like a more efficient process, not only for the production of biomass, but also in terms of economy, basically, because we are reducing the amount of inorganic nutrients and organic nutrients that are in the wastewater. So that improves the quality of the effluents that we are running off to the systems. So at the same time, we are able to recover the nutrients that are in wastewater to produce fertilizers. So at the end, we need to integrate the technology not only within the energy system, but also in other systems like the agriculture or any other aspects of the circular energy system or circular economic system that will allow us to make everything more like efficient.
Perfect. Thank you, Pedro. I don't know, Brian, Bill, Stefania, would you like to add something? Otherwise, you can start by asking the following question.
Can I say something, Laura?
Of course.
Yeah. You know that I think we're going to see very great advances over the next 20 years, 30 years in renewables or low carbon technologies across the board. You know, where I see the sort of stuff we're doing fitting into that is very much in terms of the obviously the wind side. If you look at the targets for wind within Europe and elsewhere, they imply a very, very large, you know, greatly increased amount of wind sourced energy being introduced to the system. You know, the UK targets are, you know, envisage, you know, at least 40 gigawatts of wind by offshore wind by 2030, expanding out to, you know, a minimum of 75 gigawatts by 2050. These are very large targets, but the real drivers are to keep the costs down, and that's where I see my own technology and some of the other technologies. That is what this game has to be about, to be honest, about driving down the cost of energy. Otherwise, there will be pressures which will go against the development of more renewables.
Thank you, Bill. I'm not sure actually if we closed.
May I add something?
Yes, thank you, Stefania.
Sorry, I cannot hear Laura.
Yes, of course. Sorry, I was
Okay.
away from the microphone.
So I think that also the Telegram project fits very well with the possibility to generate energy in a distributed manner, but not only energy, because from ammonia we make usually the fertilizers. So this would give the possibility to make your fertilizers on your own place. So I think there are very interesting perspectives on this point of view. But instead for the barriers, I think that we are mainly facing the problem that the present technologies have been developed in many years, in some cases hundreds years. So it is difficult now in a very short time to become so reliable and so cost effectively to be competitive to those technologies. But we have to do, otherwise we cannot make this transition to renewables.
Thank you, Stefania. I'm going to link what you said. It's like, okay, we need to achieve this, but what are the barriers that are we facing to do this in terms of innovation in the energy generation system? So we link it with the next question, which is following up to what you just said. I will ask Brian if he would like to start, but I'm not sure if he's there.
No.
A message there. Problems with connection.
Yeah, you're talking about the barriers.
With us. We cannot hear him. Okay, so let's continue. I don't know if he said anything on the chat. Actually. Okay, so let's follow up then with the next question. Should we go in the same order, or would you like to change? Like, of course, whoever wants to speak there.
I'm confused.
Okay, I may start. If you have anything to add, of course, interrupt me. Coming to the barriers topic, I think that when it comes to energy generation systems, we are all dealing with complex technology, and moving over what is already available on the market entails higher investments, upfront costs not negligible at all. And it is very specific for our project, but I can appreciate your project as well could have this kind of issue. So whenever you try to develop something new, you have to face this kind of problem. And a European organization that supports this first step, moving from a concept to a product that can be available on the market, can help companies to overcome this initial issue.
Thank you, Ricardo. Aldo, would you like
Well,
to?
yeah, I do not have too much to add. I mean, I think, as I said before, we need really a social acceptance for the changing. So we have seen with electrical cars. So the electrical car, where injecting the market in few years are becoming a quite interesting business case, but also something that moves in the direction of the green transition. So, and this because it was a large social acceptance, also pushed by the request for green transition. So I believe this is what we miss probably up to now. So we need to let the people that this is something that is important for the future more and more, and then also accept some changes. So the way we, for example, in the case of the car, we fuel the car, or in the case of energy generation, the way we generate energy, how we use the energy, on the way we transform the energy. So I believe we need to make a little bit more effort in communicating also this kind of transition to all the people, to all of us.
Thank you, Aldo. Indeed, social acceptance is going to be an important one. Are there any other barriers for your projects, or more in like overall in the energy system that you would like to mention?
Can I make a comment? Can you hear me? No?
I can hear you, but maybe not them. Maybe not in the room. I don't know.
Okay. Laura, can you hear me?
Are there any other barriers that you would like to mention? Stefania, Pedro, Bill. I hope Brian can hear us.
Well, I guess the issue we're having with our project, distribution chemicals, you typically need to do that in bulk.
Sorry,
So
Brian,
actually,
we cannot
this
really hear you well.
distribution costs either, I mean, our competitors buy gas, so it doesn't help them any either. Having this distributed network to do mass production
Of some
is actually
cameras,
going to be
but
a
I'm not sure if
barrier
that's going
or
to solve
something that we have to deal
the problem. We could try.
with. It has been beneficial in the past to concentrate your chemical plants in the economies of scale, which you won't get with the
Brian,
non-distributed
could you
distributed
try
system.
again?
So,
Okay. Otherwise, Stefania, Pedro, or Bill, would you like to add something while Bill figures out if he can speak?
I think that at the stage at where we are now with the project, there are some challenges which are technical challenges, because we have to reach some performances which should be comparable to the present industrial process, and this is difficult. But of course, we have also this problem of social acceptance, which is very important.
Thank you, Stefania.
Can I say something? So Laura, we cannot hear you
Can you hear me now?
very well. Very low. I mean, you need to be closer to the microphone, I think.
Okay, can you hear me now? Okay.
A bit better. Well,
sorry for the technical issues. It's our first hybrid event. We'll see how to improve this. Pedro,
okay,
anything?
Yeah, I would like to say that I don't think there are, at least from my point of view, great barriers for innovation. Basically, there are many really good ideas and projects going on, and innovation, I think, is ensured. But the main problem I find is probably the next step, the next topic, that is how the stakeholders, mainly the companies that could be interested in our technologies, adopt or accept these technologies to integrate in their systems. For instance, I'm speaking about, in my case, microalgae production in wastewater treatment plants. So we need to be able to integrate these technologies in these wastewater treatment plants. But for that, we need the acceptance of the people that is in charge of these plants. So we have the technology, we have the ideas to make innovation, but we need the acceptance of these companies to implement these technologies.
Thank you, Pedro. So this links to the next question, which actually also related to barriers and challenges, but now focusing more on how to bring these technologies to the market rather than developing the technologies. So this is linking to what you said, like how do we get the companies to actually, once the technology is developed, to adopt them? So do you have any comments? Maybe Stefania or Bill, you can start.
Okay.
With this, also making some, also answering to other barriers if you would like to, but also focusing more now on how to bring the technologies to the market.
Okay, can I just start on that, Laura?
Yes, of course.
Yeah, okay, thank you. It's already been partly alluded to, but there's real barriers in getting new technologies to the market and getting accepted. there's inertia in all markets. Basically, a great deal of money has been invested over a long time to bring existing technologies to the level of efficiency and effectiveness that they now have. And so there's vested interest, shall we say, in maintaining those technologies as they are. So if you bring a new technology to the market, you don't need to, it's just not being better or cheaper. You have to be much better and much cheaper before they'll be accepted. And an additional aspect to that is that it's how the benefits are viewed. The manufacturers of turbines, for example, that all they're interested in is the savings in the cost of the capex cost of the product. Yet, from a society's viewpoint, it's the actual cost of energy that matters. It's the combination of it's not just the capital cost, it's operating costs and other associated costs. But the different parts of the sector just focused on their existing the costs that apply to them. They don't take the more holistic viewpoint. So this is a challenge to be overcome. The other thing is that it's the sheer cost of demonstrating new technology. For our own technology to do it doesn't scale down. We have to go from the first demonstration in the field would have to be a large turbine, say 5 megawatts, and the cost of that is huge to do that with a prototype. So it's getting, it's getting the buy-in by the investors into this process is another large barrier, because they don't like risk, and inevitably with new technology there is risk when you go to demonstrate it.
Thank you, Bill.
Well, this topic is, as far as I'm concerned, is very much related to the previous one. Whenever you're trying to phase out proven technologies, you need that initial support to demonstrate that your idea is comparable with the current ones, and you actually can obtain better results. Without that, in the beginning, of course, there is no way to be competitive from an economic point of view, and this results then in a too high cost of energy. But once you build industrial networks to provide components and to provide the technology on a sufficiently large scale, that is already a first step, and European projects are doing much in this. And then, of course, as Aldo mentioned, uh, people have to believe your product is better than everything that is available on the market at that moment, and social acceptance can be a hard barrier to overcome. So in this, we will all have to work both from a social point of view, a communication point of view, as much as we work on the technical standpoint.
Thank you, Ricardo, for bringing like the two main points that we will need to overcome this challenge. Um, could any of you would like to add anything to this topic?
No, no, I
No.
believe we
Okay.
mentioned
Yeah.
all the most important points.
Uh, I will ask Brian again if he is able to speak, but I'm not sure we will manage. Otherwise, we will go to the next question. Brian, can you try to give your perspective here? I don't know if we will be able to hear you. Okay. I'm sorry for this. Okay, so now going for the last topic, we have 8 minutes left before wrapping up. So, considering that these technologies are very different from each other, what is the European policy and regulatory framework that could support the growth of these technologies? Is it the same for all of them, or do they fit in the same macro scenario, or would they require policymakers to go in different directions? We have 6 different projects. Do you think that they do fit in this same scenario, or different policy advancements should be made for each of them that could benefit one and not others?
I may start because probably we need to face actually in City Solar, but also another project where we need to develop new materials. I believe we need a change in the way we consider um, problems with material, with new materials. For example, in our case, we have a technology to use a little of lead, which is, if you make, just if you consider lead by itself, I mean, could be, I mean, quite problematic for European. But if you put this in a LCA and then you compare the LCA with the technology, with other available technology, is much better. So I believe European policy should move also to consider the entire cycle of the life cycle of the product and compare them on the same food. So, for example, the new standard like eco label, eco design are moving in this direction, and this will allow, I mean, to make innovation more fast and to make the innovation penetrating in the market. If we still stay with the old standards, which are really, it's quite industrial standards, which is very related to energy standards. I mean, we will move very slowly, and we will not match the goals for 2030 and 2050. So, what is really missing, I believe, which is one of the barriers, is really this kind of new strategy for products in Europe that should allow a more fast changing in the technology.
Thank you, Aldo. Do the representatives of the other projects agree that these changes are needed towards a regulation that allows to measure the take into account the whole life cycle of the projects they're developing? Is this the direction that you think that should be taken, or do you have other ideas? Stefania, would you like to add?
Yes, I think that this may be one direction, but also I think that usually when you go from technology that is developed in the lab, you have the problem that companies don't want to invest too much and to risk, as also Bill was saying, a lot, especially in terms of money. So I think that Europe should help to bring together the laboratories and the companies and try to find a way to go faster from the lab to the market. Because I think there is a lot of work that has to be done for optimization in order to go to the market. And usually laboratories cannot do this by themselves. So we need some help in this sense.
And how do you think the help in which, how could the Europe and the European regulations could help the laboratories in this sense?
I think that in some way the new Horizon Europe is trying to do this because they are trying to put more together industries and companies with research labs.
Thank you. Bill, Pedro, or Ricardo, would you like to add anything?
Yeah, just thank you, Laura. One more consideration. I think we all agree that supporting laboratories and companies to innovate it is important, but we live in a world that is basically customer driven. Aldo mentioned before the example of the electric cars. If you convince the customer that a new technology is better, is important, they will start wanting it. And at that point, in such a fast-pacing world as we live in, making innovation will become easier. At the moment, I think we still live in a conservative country, in a conservative environment. If you push the customer to request a product, at that point, companies will be forced to innovate even faster than what we are doing.
Thank you, Ricardo. Pedro, Bill, would you like to add anything? We have a few more minutes left.
I'd just like to take up on that last point. I think it's a bit wider than just getting the customers on board, as it were, to push the companies to go in the right direction. I think it's organizing the market a bit better. There are different types of markets involved in the energy sector and so on. There's what you might think of as the very large scale generation of power, which is aimed at over a large region, say, providing base power, etc. But and let's call this transmission. But then you've also got the distribution level, where you're down to more local level and you're delivering to customers directly. But where we're going forward to is a situation where we're going to have energy storage, etc. Which to back up all these renewables, etc. So I think there's a need to approach what I would call a systems level approach. Now, when people talk about the systems levels approach to energy, think about the whole provision of energy to a nation or whatever. But I think we need to break this down into various layers, and I think that needs to be recognized by policy people and put in place the mechanisms to create markets through this multi-layered level, but taking into account systems levels approach. In my own area about wind, if we're going to have energy storage involved, where is that going to be? Is it going to be onshore, or is it going to be embedded in offshore in the wind farms? Is it going to be embedded in the turbines themselves? How do you use that most effectively, etc.? That level of integration is what is going to reduce the energy costs over the next decades. And I feel there's a lot of warm words talked about things at that sort of level, but I don't see the frameworks there. I think we need to have some sort of more direction of that through policy and the regulatory framework to try and improve that holistic level of thinking and bringing the technologies together, because we all complement each other in many ways, and that's going to be one of the main drivers, is exploiting that over the next decade to address all issues: more reliable, more cheaper energy for all purposes.
Thank you very much, Bill, and thank you all for all the interesting insights that you brought to this topic. And luckily, we do not have time for any more discussion or questions, but of course, all those that are connected to the Hopping platform, you can really request connecting with any of the people connected, and of course, you will have the contact of each of the speakers afterwards. We will share the slides. And of course, there will be networking for those here physically in Rome. But anyway, we will continue the conversations. I will come back to all the speakers to really push this forward and really go deeper into these questions. Thank you very much for joining, for contributing to the development of this workshop. We will improve for future occasions the technical issues. So that's all. Have a nice day. Thank you.
Thank you.
Bye-bye to those online. Thank you.
Bye.
See you soon.
Yeah, thank you, Laura.